Good morning, everybody, and thank you all for joining this fourth and final session of our Plastics 101 series. My name is Nikhil Venkat. I am an application engineer here at KETIV. So, what we're going to do here today is not only talk about um, what we're going to do on this particular webinar, but also kind of back up and touch a little bit on what we did in previous sessions, and actually jump to the software today. So it's a slightly different approach than we've taken in the previous sessions if you have been following them. Now, once again, why we're here today, why KETIV is here presenting this webinar today. The whole idea is to make our partners more competitive and successful through training like this, guidance, support, and of course, technology in the form of software. Now, KETIV is also an Autodesk specialized, Autodesk Moldflow specialized partner. What that means is we have the expertise to train, implement the software, and even consult with you with a team of trained engineers and account managers, with, of course, constant support and backing from Autodesk, especially folks like Brian. Now, in the last session, what we talked about specifically was how optimization will help really, light up your designs, whether that's design for a part design, whether it's a mold design, whether that's designing your process. The whole session was about how design of experiments, parametric optimization will actually help you make these better decisions and give you a lot more, well, I'm not able to find a synonym at the moment, but give you a lot more insight into the actual process that's going on, even let you kind of consider things that you don't normally see physically before you actually start with any prototyping or any molding process. Now, speaking of that particular molding process, if you joined us in one of the previous sessions, you would have seen the slide where we go through this entire process, right? So you start with a concept, you create a part, you create a mold, you build the mold, and finally, once you're happy with all the parameters, once you're happy with the process, you put that into production. Now, you may also remember that while we're doing this, we're trying to answer a few questions at each stage of this, right? So in terms of the part design, what's the geometry, manufacturability going to look like? How's the material going to behave? When you get to the mold design, you're looking at cooling layouts, flow paths, and finally, when you're of course talking about production, you're talking about cycle time and what the part quality is going to be, etc. Now, again, this is a number. Sorry,
I was just going to add a comment that, this to me, every time I look at it, the real striking point is that it's evolution of details and also variation. Of course, when you start with a single part or design concept, everything's less complicated, but you can make some really great choices with those assumptions. You don't want to negate the amount of detail that's going to come downstream, because you can still get fooled. A single part only feels great, but what happens when you add details like runners, gates, cooling? It's an evolution of variation too. If you can get it more uniform at the part level, you have less variation when you get to these other complex details. So kind of interesting trend of details and variation, which variation is the devil when it comes to plastics.
Absolutely. And it's kind of layering on top of each other, right? So if you make a certain design decision, the positive consequences of that decision tend to follow you through the process. But also, if you make a bad design decision early on, that tends to snowball and really become a massive problem once you get down the road. So
Absolutely.
yeah, so it's layering up, and as you mentioned, variation is a big part of this, and that variation just keeps increasing as you go down the process. So that was part of why we talked about optimization last time around, because it's important for you to be able to make these decisions early on and to figure out what the best possible design or process decision you can make at a certain stage would be. Now, the questions here, of course, are for the most part yes or no questions. You know, is this good or bad? Is this doable or not doable? You're not always going to be able to answer those questions. So, you know, in a single word, you wouldn't be able to go yes or no, or you wouldn't be able to qualitatively explain what's really going on here. So, a lot of you may have seen, especially with MoFlow Insight, that there's a whole bunch of results that I wouldn't say don't care about, but they're not something that you have actively explored in the past, and they're not something that you think you need, and it's really overwhelming. So you've got your fill results, you've got your fill and pack results, you've got your cooling results, and then you've got your warpage results. And I believe filling and packing, just that portion alone, has 36 results, if I'm not mistaken, Brian.
Yeah, absolutely. It inspires an old term, paralyzation through, over analyzing, too much data.
Yeah, absolutely.
Paralysis by analysis is the old term. And in reality, you probably need, go back to why you're running the analysis, right? If it's a general, if it's specific quality criteria, great. Then you kind of know what you need to look at and boil it down. But if it's just general health of the design performance, then you have to really go back to the criteria that makes that part perform. Is it cosmetics? Is it dimensional, form, fit, function? What are those key components for performance? And that's how you boil down the overwhelming amount of results that there is. And getting back to that earlier point you made, it's like, you start with a single part and it fills. Great. Just move on, right? Nope.
Yep.
It's you need to internalize that and then think about the scale up downstream. What type of feed runner system, how many cavities, that's all part of the scale up factor that needs to be considered early on as you make these choices and pick the right results.
Yep, absolutely. Thank you for that, Brian. So question, of course, is do you have to review them all, as Brian mentioned? Probably not, right? And thanks, Brian, for stealing this whole slide. And
I was setting you up, man.
But no, as Brian mentioned, it's important to keep in mind the objectives for the analysis itself and allow those to really determine what results are important and what are not. It's not, if you have a set of results that you go through every single time, then that may not be the best approach, right? The approach must be geared towards the objectives of the analysis, the goals of the analysis. And based on that, if, for example, if part quality is something that's important, maybe you want to look at, just pressure and temperature as your fundamental first pass result check. If part strength is important, maybe you want to look at sink marks and weld lines, and aesthetics also kind of gives you, or those results will also give you an idea of what the aesthetics of the part are going to be. If you've got, shrinkage issues historically, or that's what you're seeing with your prototype, maybe you want to look at the shrinkage and the frozen layer. So there's a lot of different result combinations, result sets that you can look at without really having to go through every single one every single time, right? And again,
The other mind-blowing thing to this is you can customize each one. So
yes.
there's a subset of these individuals that gets exponential. So I think like one of the points is how do you boil it down? What are your go-to
Hmm.
results, and how do you customize to tell the story or to get the root cause? It's definitely you have a lot of choices.
Yeah,
That's good.
sure, for sure. And again, with the one thing that I didn't mention that Brian, you kind of touched on here with customization is a lot of these results. Some folks prefer the actual visual approach. Others would like to see a plot and an actual graph, something that they can export and play around with. So depending on how you want to see it, whether it's a slice plane or whether it's a 3D animation or whether it's a graph, you do have that option with most of these results, and it, it's going to come down to what works best for you. So we'll go over some of these results now and talk about what you should be looking for, and we'll do this in brief before we jump straight into the software. The first thing I want to talk about is the typical filling results. What should we be looking at? Big ones, of course, are fill time and pressure at VP switchover. VP switchover is basically just the point at which it switches from fill to pack, right? There's nothing crazy about that. It just switches from having filled to the packing phase of the process. So when you're looking at fill time, the big ones are, of course, does the part fill? Does it fill completely, or is there a short somewhere? Is there some kind of race tracking or hesitation effects? You can also look at your weld lines and your air traps to figure that out. Same thing with a pressure switchover. You're looking for a balanced distribution of pressure, uniform distribution of pressure. Now, you can keep going through the different results. Temperature flow front is a big one. So if you see that variation being too high, that's clearly a problem, and that's something that needs to be addressed. The bulk temperature at the end of the fill, if that variation is too much, if there's going to be shear heating in the part, then yes, again, that's something that needs to be addressed, and maybe excuse me, maybe even focus in and zero in on the cooling part of it at that point. And
Yeah, and it's a game of averages, right? So as you go from a single part to multi-cavity, you've got shot-to-shot variation out on the manufacturing floor, cavity-to-cavity variation, material lot variation. So yeah, narrowing this down in the theoretical world is a lot easier to do than the real world, and that's kind of the game you have to play. It's like, how do I make this as uniform as possible so I don't have quality criteria fighting each other out on the floor?
Yep, absolutely. And all this while keeping in mind your molding and manufacturing capabilities. So as I mentioned, one of the things that we're also concerned about, if you're looking at weld lines for part strength, or you want to look at the frozen layer, frozen layer basically just means how much of it has how much of the part has actually solidified or stopped flowing, um, while the rest of it is actually flowing, right? So if at the end of the filling phase, if that's more than 0.25, the frozen layer fraction, that's a big red flag. That's something that we need to address. Maybe look at part thickness at that point, or adding another gate. Weld lines, again, there are certain areas where you do expect to see weld lines, of course. In this case, on that particular cover, as you can see there, every kind of gap, every discontinuity in the geometry is likely to cause some kind of weld line. If that's something that shows up in the middle of the part, or if that's going to be in an area where the part's going to be most stressed, then maybe that's not the best approach to molding that particular part. Maybe there needs to be a different approach, You may have to go back to the drawing board for that, but you have that information beforehand, and that's the big takeaway.
Yeah, that's another great example of customizing a result. So that weld line, overlaying the flow front temperature or pressure kind of helps give you that ingredients of that weld line. Was it hot to create better bonding? Was it at higher pressure to mingle the polymers together better as far as weld line strength? So it's a great example of how you can customize results.
Yep, absolutely. And that's one of the things that I absolutely love, overlaying results. So particularly with the weld lines, there's you can overlay that with the temperature. You can overlay that with just the fill time even, and
Yeah, that's
every
one of my favorite. Yeah.
yeah every one of those overlays is going to give you different varying levels, varying degrees, varying types of information, which I think is great. Similarly, if you're looking at air traps, you know, again, if are they going to be in areas where there are no vents, or do they form in the middle of the part? That's obviously a big red flag. So that's something to address. Time to reach ejection temperature. Um, Again, is a variation in the time that it takes the part to reach ejection temperature. Is that too much? Is that a really high amount of variation, or what is that variation due to? Is it just sheer heating, or is it due to wall thickness issues? We get to answer these questions um, through a lot of different approaches, different tools that we have at our disposal, and that's the point of this. Now, similarly, when you're kind of jumping into the packing side of the results, you're looking at things like volumetric shrinkage. Right? This shrinkage is a big deal. It's something that I'm sure every plastics person has run into at some point. Is if that variation of shrinkage is too large, if that shrinkage is starting to bleed over into warpage, then yes, that's definitely a concern and something that needs to be addressed. Um, the one of the biggest thing for packing is the pressure. The biggest quantity that controls packing is the pressure. So the pressure plot will let us understand, what that pressure decay looks like. If that is too fast, if it's too quick, then certain areas are likely to be not packed fully. So again, it, whether this is a post prototyping um, simulation or post molding simulation, or whether you're doing it up front, you do have to answer these questions at some point, and you might as well do it up front. Gate freeze again is another big one. Time to reach ejection temperature, we kind of went over that already. Um, is a cycle time, much longer than what you actually see with the result. So if it is, then maybe you do have to consider some other quantities. Maybe you need to consider some other physics that's going on in there that you hadn't previously considered.
And gate freeze or, freeze around a gate region pretty much, cuts off compensation. So it could be one of the sources of high variation of volumetric shrinkage. And we know we always got critical dimensions on a part. And if there's high and low areas, you're not going to get away with cutting a single shrink value on a mold, or at least your dimensions will start varying region to region. And as you mentioned, if you get enough differential shrink or other components, you can then see warp, which is a much more difficult issue to combat.
Yep, absolutely, and that's another part of this, right? All of these results are likely related to each other, or most of them are likely related to each other. So really, if you're going to modify something based on just one result, chances are it's going to affect some other result. So it's important to understand why things are happening and not just what is happening. And that's why we go through a number of results. Again, that doesn't mean you need to go through every one of those 30 odd results, but you, depending on the things that are important, depending on the things that you're seeing, you will have to go through a combination of them.
Exactly. That's really well put. I mean, when you see results connecting with each other, the trend becomes so compelling and overwhelming. You see this making sense when you collect the varying results telling you the same thing over and over again.
Yep. And that's also where optimization routines come in, right? So once you have that inkling of a connection, it might be worth exploring what result or what particular result is contributing more to what you're seeing, or what particular quantity is contributing more to the certain result than just shooting in the dark. So um, today's a very short fairly short presentation. We will jump straight into the software after this. But before we do that, I did want to mention an event that we have coming up starting tomorrow. So it is a digital workshop that connects you with one of our engineers. And the idea is to talk about what the idea is to talk about, a particular project with particular issues that you're having. And we'll spend some time, an hour maybe, just going over, different issues that you're having. Are there certain things that you're trying to fix with the software that you haven't been able to? And really, the idea behind this is to see if there's technology that you own already that you can leverage, you can use to solve some of these problems. The idea is not to sell you more things, it's not to get you to buy more things. It is to figure out whether, there's certain hidden features and technologies in the software that you already own, um, whatever level, degree of Moleflow that is, whether that can actually help you with the issues that you're having. So there is a way to sign up for this. I will post, actually, let me do that right now. I'm going to post the link in the chat window so everyone can access it. Now, remember, keep in mind, this is, there are time slots on there that you can choose. So as soon as you pick a time slot, that one goes away. So make sure you do that as quickly as possible. So I'm just going to post this in the chat window right now. So make sure you do this as quickly as possible. We do see a few slots disappearing already. So go ahead and do that. It does come with its own prerequisites, of course. Make sure you have a particular part that you want to work with, or a particular design or process that you want to work with. And try and make this a slightly larger initiative, right? So whether that's going to be a team-wise initiative or a company-wise initiative, feel free to discuss this with your coworkers. If you can come up with a particular design that you need help with, then we'd be happy to jump in and help with that. And I think it would be a lot more productive as well. Just so we're not treating this as an open-ended kind of training class that just goes on for an hour, right? So let's make this as targeted as possible. So see if you can bring a part in. We're of course happy to sign NDAs if that's ever a concern. So feel free to bring in a part, and we can start working on that. And again, the idea is it's not just this 1 hour and done. If we need more time at the end of this, we're happy to work with you after this 1 hour workshop as well. Okay. So we'll go straight into the software here. Let me pull that up real quick. Let me know if you can all see my screen, or rather, let me know if you cannot see my screen. What I have open up here is MoFlow Insight, and this is going to really contain all the dozens of results that you saw previously. So there's two, very distinct approaches here. There's of course MoFlow Advisor, MoFlow Insight. We'll jump into Advisor in a second. But with Insight, what I have here is a snap cover. Now this is a full-blown analysis, right? It's got its own runner system, not just an injection location. It's got its own cooling channels and everything. So it's not just an injection location. This is the whole 9 yards. And you can see here that I've actually run a fill, pack, cool, warp analysis. So I have the fill pack results, the cooling results, and the warpage results as well. So some of the results that we're looking at, some of the ones that we talked about already. The big one is, of course, fill time. So you can go straight into your results environment and just look at an animation of the fill time, make sure it all fills evenly and uniformly. And as we were talking about, overlaying the weld lines is always a great result, right? So depending on what your flow pattern actually looks like and what the weld line growth actually looks like, we're able to visualize both of them together. Okay, so that's the, sorry, I just realized that the meeting link I posted was private. Sorry, I didn't include everyone. Thanks for that, Brian.
I didn't want to interrupt you. Yeah, no worries.
Thank you. So, yeah, the idea here is, again, to understand the propagation of these weld lines and how it's related to the actual filling of the part. If you see there's no issue with the filling of the part, but you see there's, weld lines all over the place, then that's likely because of something else.
Yeah,
So,
no two weld lines are created equal. Just how the flow front comes together, maybe backfills towards the interruption in flow. These are dynamics that can make, air entrapment or more difficult to get a good weld. Does it butt and stay stationary, or does it move downstream? These are all dynamics that are kind of great to visualize with overlaying different results.
yep, absolutely. And again, depending on, I guess what sort of results you want to be looking at, right? You can, for example, if you're looking at the clamp force, you're looking at a plot, and you have several different options available to you. You can actually export these plots and do all kinds of things. But
another great like XY plot is and a lot of people like skip this, is the ram speed recommended XY plot down like 6 from where you're at. Yeah, under there. Yeah, that's based on a constant velocity, so it's like feedback in a result form of like what would provide a more uniform flow, velocity flow front. Kind of interesting.
no, that's, yeah, this is definitely one that a lot of folks will use as well. Couple other things, again, if you're interested in the aesthetics of this, maybe look at location of sink marks, if any. If you don't have that, that's great. If you do, you will be able to sort of visualize the effects and push them out into
it's
a different.
it's a good thing to point out here is the sink mark estimates are based on projections, so ribbing, gussets,
Yep.
from the non-cosmetic side to the cosmetic side. In this case, we don't have any. So another connecting result as far as building that story, would be moving to volumetric shrinkage and kind of looking at where are the high spots. So we kind of use that term sink mark as a general distortion to a surface. In MoFlow, it's actually a sink mark index is related to a projected, detail like a rib, boss, gusset, etc., where volumetric shrinkage can be another tool to use to see where you're likely to see the most distortion. So whether that is a ripple in the surface um, or a printed like printout readout of a boss or a gusset on the backside, it can be used hand in hand. So two results that I like to combine, especially when there's, in this case, a lack of projected detail like ribs and gussets. We would go right to the volumetric shrinkage.
Yep, absolutely. Thanks for that, Brian. The one of the big ones, and Brian, you're gonna love this, is the velocity.
Thank you.
So the velocity result is one of these it's these, I guess, hack results. Don't mean to call you a hack, Brian, but it's
Yeah,
what
no worries. It's truly the biggest bang for your buck. If you want to
it is.
take a look at variation through flow, the filling, into compensation, so the packing phase, as well as solidification as these arrows turn red to blue, flow
Mhm.
fronts are moving faster or slower. And that uniformity is important because everywhere you get a change in velocity, temperature, pressure, you get a change in cosmetics and physical properties. And then as this starts to move during compensation, which it does, we're dealing with compressible flow, you can also see how certain areas are being overpacked or how a weld line may flip in the undercurrent. Or in the case where the arrows are disappearing, now we see solidification. So one of the biggest bangs for your buck, my favorite result, velocity. You do need to scale it though. I think you already did, Nikhil, here, because default is, across the whole gamut and it's a very high max value. So if you drop way, way down, real low, you start to see the colors pop. And visually, like when you clip through the initial filling, you see areas are moving fast and areas are moving slow. What can you do about balancing that out?
Exactly, and I think if you learn to read this result, it's going to save you a bunch of time just going through number of different results here.
Boy, that is the magic word, right? And today the software is so easy to use. Getting results used to be work. Now it's not. Now
Yeah,
it's more around what do you do with these results? They almost come to you with no effort at all. But how you interpret them, how you use them is truly the magic.
no more punch cards and readouts.
Hey, you calling me old?
um, yeah, notice how I didn't answer that.
Exactly. I know you don't really know what a punch card looks like, but I do.
Oh, I've been using Nastran long enough. Um, anyway, so like I said, this one comes with with some bells and whistles. So this has the coolant temperature as well. So this
You
has
might have
some.
those layers off.
Oh yeah, there we go. So yeah, this comes with the coolant temperature and information and results related to the cooling channels as well.
And this is detail. You can, if you're a processing engineer, you may want to look at these specific results to, say, a project engineer. You really care about, is this going to cool apart uniformly so I don't get distortion, and how fast can I get this out of the mold? So, time to reach ejection. But it's compounding. We're adding variation in mold temperature now with this cooling analysis, that's going to have some impact on the final shape and shrinkage. Good example of building detail.
Yep, absolutely. Um, so, you know, the idea behind all of this and the reason we're talking so much about the different types of results that we have in here is that you have so many results, right? So you've got a lot of these things. They'll all give you different pieces of information. Some definitely more relevant to your particular study than others, but all in all, you do have a whole bunch of this information. Now, again, if you're using Insight, then you've got the ability to kind of push this out. If you've got a, just look at the warp shape on this for a second. Um, you can always push this out into a CAD file and then move that, play around with that CAD file, maybe run a residual stress analysis, and you'll be able to understand what the residual stresses in the part are. So you have a number of visualization options in here, and you can always, of course, select a specific result. Let's say, I don't know, shear rate. Well, yeah, let's do something like average shrinkage. I can always go in and add a report image or report animation to this, right? So you have easy ways to export these results. You have quick and easy ways to excuse me, quick and easy ways to access these results. The only question is, what results do you access? That's of course going to um, take some time to understand, but always start with the velocity. You know, it's one of those with the fill time and the velocity. You know, there are two main results that will give you a lot of information in one go, and if those aren't looking right, then you can go straight back and fix what's wrong, or you can dig straight or dig further into that particular issue. All right, so we'll jump into Insight after this. I'm going to let Brian share his screen.
You'll need to, there you go. Thank you. Okay. Well, so the wonderful world of Insight versus Advisor, mainly Advisors kind of in your face as far as guidance or advice on what you're setting up. It's the more casual tool. It's using a similar engine, but whether you're an Insight or Advisor, there's always a place I like to start, and it's really just a 20-minute max kind of workflow as far as assessing the geometry, assessing where you may want to gate this, and looking at your material and material choices. Those are the three key variables that really make up a lot of the issues we see downstream as far as manufacturability. Um, if you kind of look at the the geometry itself, um, we've got some things that we can discuss. So by far, wall thickness variation is the one diagnostic, if you only had one, that you would go to, because it tells you so much about how the mold or cavity will be filled, where you're going to see different thermal loads as far as thickness versus thin areas, flow resistance, um, areas that are going to hold up the cycle, economics. And this is all simply done with one result as far as internalizing thickness variation. Did I core out a boss appropriately? In this case, no. Do I have very thin areas where the flow front's going to pass by and hesitate and perhaps short, or have relatively low shrinkage versus high shrinkage, so blue to red. Um, not just pretty colors, but stuff that we can internalize and then build upon in regards to, what's going to happen next with the next result. Does it correlate to this thickness diagnostic? There's a couple, steps. So looking at geometry, draft and undercut is the beginning of how we determine, can we put this in a mold and get it out, right? Do we have geometry aspects that are going to be difficult to um, mold, flow? And from there, we can also assess, well, based on this geometry, where would I gate this? And that may be a combination of uh, things that we want to look at there. So when you look at, where to gate it, I may have areas where I know I don't want to gate. So we can quickly like window that area and then see, based on flow resistance and number of gates, where is this ideal place to place 1 gate, 2 gate, 4 gate. And this is often quite, amazing. It actually is an algorithm smarter than me. I never can beat this as far as flow resistance or required pressure to fill the part, especially when you go into multi-gating situations where you need to extend the flow. And here I prohibited the center, so it still, prefers centroid, but it's also looking at geometry attributes, flow resistance. Centroid will generally cut the flow length in half, which is a big component to required pressure. Again, that's how this is working for you. More importantly, I can then choose that location, and this is where advisor is kind of guided. So I can go to that location and actually kick off a flow analysis. But before I do that, quite often what I want to do is figure out what this geometry and gate location and material would like to see as far as a process recipe, right? And so we can get that feedback in regards to a molding window analysis. So, given that geometry that I started with, now I can explore the dynamics of the gate location and the material chosen in regards to what is the ideal process window for this, and compare 2 different materials. Now, these are 3, key process parameters: fill time, melt temp, mold temperature. And my little indication over here tells me like what I'm looking at, what I should be looking at, but green is, preferred, yellow is feasible, and then red, I'm headed towards, high stress, short shot, bad things. And there's several ways that this can be used. One, again, I could just go to the center ideal injection time, mold temperature, and then kick off a flow analysis, or I can do some comparisons. So this is material A versus material B. Same family, but they're going to process different. One's going to give me a wider process window. And then we can look at comparisons of gate location or thick, thin geometry. How aggressive can I be with the wall thickness before I run into a very, very small processing window. Couple different ways to use this as a comparison tool, or just an initial kickoff to a flow analysis. And let's see, let's go with this. We'll open this guy up. A great example of that traffic light type result we just saw in the molding window is confidence of fill or a quality prediction. So a lot of people just run right to flow, the fill result, and go, great, it filled, I don't have a short, super. But digging into, other results like a quality prediction, and this is based on, melt properties, shear rate, shear stress, temperature, rise, gain. We can dig into these areas and find out a little bit more by examining these areas. Why are they yellow? Why are they red? If we go over to the quality or the advisor, the result advisor, we can see the recipe at which this was created. Again, dynamic help is kind of in my face here, telling me what this result is, how I can use it. But I also got a troubleshooting guide here. So this area is yellow because of a high shear stress condition. This is part of the material makeup. So that's in the material model inside of mold flow. So kind of a threshold or a speed limit. It doesn't mean that, it's like driving down the highway. It doesn't mean you're gonna get a ticket that day for going 10, 15 miles over the speed limit, but there may be a day where you're going 5 miles over the speed limit and you do get that ticket. So it really depends on the application and the quality criteria as far as how aggressive you can be. One thing I can say is, like, for shear stress, shear rate, it's putting the molecules in tension. So those are areas that are prone to chemical attack or breakage because they're in tension. And so we want to look at that from a mechanical level. A cosmetic aspect could be even more severe. So we might have to back down on this, threshold as far as what is the max level is arbitrary. You need to really use this as a guideline to your specific application. That being said, here I can kind of get more advice on what should I do for this high shear stress area and go into the different aspects of raising the mold temperature, reducing the flow rate, things of that nature. Okay, so I'm gonna clear the deck here and I'll do one final. So in this particular case, we're kind of comparing thick versus thin, trying to reduce the cycle time and sustainability, reduce our material, all that good stuff. And I'll just do a
By the
warpage
way,
compare. Yeah,
sorry, Brian. If you don't see the dynamic help, then you will likely need to download it. So you just hit the question mark right next to your name on the top right of the screen, and you hit the drop down, and you should see download offline help, and you should be able to download that.
Yeah, so yeah, that's a great point. That's something that we did recently to improve, like, hard drive space usage. But for advisor users, I think it's kind of intended to come along and guide you. So this is a bigger story as far as this demo part, this game controller. But in reality, that thinner wall section that had that high shear stress is not as stiff, and that's one of the components of, does this geometry hold up to shrinkage? Well, stiffness, that's why we add gussets and ribs, help keep things in line. In this case, the thinner wall, was more prone to warpage. You can see areas going above the tolerance that we kind of plug in here to see the threshold. And yet on the other side, where we increased the wall thickness, we made this a stiffer kind of matrix. It's holding up to the shrinkage better, so less out of shape distortion than the thinner version. Always consequences with our design choices, and this is, can be an aggravating one. Warpage is definitely hard to combat when you get to manufacturing. Quite often it will mean economic losses, longer cycle time, post-molded shrink fixtures, all that stuff you don't want to have to do. With that, I'll turn it back over to you. We're kind of running up close to the end here.
So once again, thank you all for joining, and hope to see you all soon.
Okay, thanks, Nikhil.
Thanks, Brian. Bye.